Hey everyone, today we're looking at Chapter 7, Solving Systems of Equations. This is our first lesson in Chapter 7. A linear system is a system of equations that has two or more equations using the same variables, and the solution is the ordered pair that solves each equation in the system. You've seen in Algebra 2 that we can solve graphically, by substitution, by elimination, which is sometimes called linear combinations, and also matrices, which we'll explore in this unit. Whenever we're talking about systems, sometimes we like to categorize the systems by names. So you can have three different situations occur. You can have lines that intersect with one solution, and we name that system consistent and independent. You can have parallel lines that have no solutions at all, and we name that system inconsistent. And then you can have the same line coinciding with another line, one on top of the other, that would have infinite solutions, and we name that system consistent and dependent. There's a process, I call it a four-step process. I'll let you read through those in your notes on your own, but I'll model those as we move along. So hopefully you have some system to name your equations. I like to do it with just a red pen and call them equation 1 and equation 2. And if you notice, equation 1 has a negative y and equation 2 has a negative 5y. So if we multiply equation 1 times negative 5, I just want to multiply through by negative 5. That'll give me an equivalent equation, negative 15x plus 5y equals negative 35. And when I add that to equation 2, this should seem very familiar to you. We're going to end up with negative 13x equals negative 26. So x is equal to 2. And then if we back substitute into equation 1, 3x minus y equals 7. So 6 minus 7 is equal to y. Y is negative 1. And we have a solution that is two intersecting lines, a consistent independent system, and they cross each other at the ordered pair to negative 1. In example 2, again numbering my equations 1 and 2. If we multiply equation 2 times negative 3, we'll have 6x plus 3y equals 14, and negative 6x minus 6y equals negative 15. When you add them together, we have nothing left on the left side and negative 1 on the right side, and that's a false statement. So I'd like to say if my x's and y's disappear and I have a false statement, then we have parallel lines. There's no solution. That's an inconsistent system. Now you could have tried that by solving for y, and you would have found that in slope-intercept form, they would have had the same slope and two different y-intercepts, and that would be another approach to take as well. In example 3, you might already see it that equation 2 is just 2 more than equation 1. So if you take equation 1, 3x minus y equals 4, and you divide equation 2 by 2, you're going to get negative 3x and plus y and negative 4. So again, on the left, nothing is left on the left, and 4 minus 4 is 0. That's a true statement. All my variables went away, so they're the same line. They're coinciding. One line sitting on top of the other. And that's known as a dependent solution, a dependent system, And there would be infinite solutions. So we have infinite solutions. Every point on one line is the same point on the other line. In example 4, we have a circle here and a parabola here, and in a minute we'll look at the picture. So taking the equation of the circle and moving the x squared over with the y and adding the two equations, we want to add like terms, so the x squareds are gone. We got y squared plus y equals 12. You take that 12 to the other side, and we have a parabola that we can factor. Factors of negative 12 that add up to positive 1 would be positive 4 and negative 3. So our y values would be negative 4 and positive 3. And then we're going to use equation 2. So if you substitute negative 4 for the y is x squared minus 4, then x squared is 0. So x is 0. So we have 0, negative 4. And then repeating that, if we substitute 3 for y with x squared minus 4, then x squared is 7. So x is either positive or negative, square root of 7. And we'll see that in our picture on the next page. This was the first one. When x is 0, y was negative 4. When x is radical 7, y is 3. And when x is negative radical 7, y is also 3. So we had 3 solutions. Now in this example, we have a cubic and a line which is 1/2 x minus 3. And I believe I have that on my calculator here. And I've already pre-found the solution. So this first one, using the intersect feature, I'm going to call that point A, and this one point B, and this one point C. So point A, that would be this one, point B, and then point C. So point A intersected at negative 2 3/4 and negative 4 3/10. Point B intersected at 48 hundredths and negative 2.76. And then point C intersected at 2 28 hundredths and negative 1 87 hundredths. So those are my intersection points using our graphing utility. In question 6, we have a cubic function and a parabola, and they're both equal to y. So we can set them equal to each other since they're both equal to y. And that would eliminate the y's, and then we can solve for the x's. So collecting like terms, x cubed plus 2x squared minus 8x will be 0. Factoring out an x leaves us with x squared plus 2x minus 8. And then 4 times 2 will give us 8. And if we had 4 positive and 2 negative, they would add up to be that middle term 2. So we have 3 places they're going to cross, at 0, at negative 4, and at 2. But we want to come back here to this equation and solve for y. So when x is 0, y is going to be 0 in this case here. And when x is negative 4, we got 2 times negative 4 minus negative 4 squared. So in that particular instance, our y is negative 24. And then finally, when x is 2, y is 2 times 2, that's 4, minus 2 squared, that's 4. So in this case, y is 0. That gives us 3 ordered pairs for our solutions. The first is the origin, and then -4, -24, and then finally 2 zeros. So this particular system, I didn't graph it, but this particular system has 3 points of intersection. And those were pretty straightforward, easy to find. Okay, it's getting a little harder now. We got 3 equations and 3 unknowns. So we got 1, 2, 3. And first I'm going to take equation 1 and equation 3, and we'll add those together. So we've got x plus y plus z equals 5, because I looked down this column and I noticed that we had opposites on equation 1 and equation 3. So that makes it pretty straightforward. Adding those together, we're going to get 4x, 4x plus 3y, the z's are gone, and that gives us 9. Then next I want to take equation 2 and equation 3. We'll multiply equation 3 by 2 so we can get that additive inverse there. That gives us 2x minus y plus 2z equals 1. And then 3 times 2 is 6, and 2 times 2 is 4, and 2 times 1 is -2, and -4 times 2 is -8. So we get 8x and 3y and -7. So we'll name this equation 4 and this equation 5. So we want to do something with equation 4 and equation 5. So how about if we take 8x plus 3y equals -7, and we'll multiply this one through by -1. By -1. That's the danger here. Oh wait, I messed up on this. I missed that negative right there. Don't let me get away with that. Equals 1, -1. So we have 4x is -8. So x gives me -2. And then we can back substitute. Let's back substitute into equation 4. So 4 times x plus 3 times y is 1. 3y is 1 plus 8, so 3y is 9, and y is 3. And now we just need to go back maybe to equation 1. X plus y plus z equals 5. X plus y plus z equals 5. So 1 plus z is 5. That means z is 4. So our ordered pair is going to be alphabetical order: x, y, and z. So these 3 equations intersect on a 3-dimensional plane at that ordered pair. So I would recommend turning off your video and trying this one on your own, and then coming back to check with me that you had the same answer I did. See you in a minute. Okay, I'm not sure which method you used, but here's what I did. I took equation 1 and 3 and eliminated the z terms, which gave me equation 4. Then I used equation 1, multiplied through by -2, added that to equation 2, and that gave me equation 5. Since the y's were opposite, I added equation 4 to equation 5 and found out an answer for x. I went back to equation 2 and put 1 for my x, so -1 plus y is 2 when y is 3. And then I use the 1 and the 3 and put that into equation 1 and found out z was negative 2. So that's not the only way to work it, but that's the way I worked it and got that solution for example 8. Now, in example 9, we're going to use the standard form for the quadratic ax squared plus bx plus c, and these are our x's and y's here. So these 3 points live on some parabola. We want to find that parabola. So what I did was said to myself that I could write a times the x value squared plus b times the x value plus c has to be 11. And that gave me a minus b plus c equals 11. So that's my first equation. Now the second equation, we're going to repeat that. A times the x value squared plus b times the x value plus c has to equal 5. So our second equation was 4a plus 2b plus c equals 5. So that's equation 2. And then finally, our third equation for this complete system is going to be using the points 1 and 3, or the ordered pair 1 and 3. So a times 1 squared plus b times 1 plus c has to be 3. And that equation is a plus b plus c is 3. So using those substitutions, we have a system of equations, and it just kind of goes that we should add equation 1 and equation 3. Since they're already opposites on the b term, our plan of attack will be to eliminate all of the b's. So here we're adding 1 and 3, and it's going to give us equation 4, which will be 2a plus 2c equals 14, and they're all divisible by 2, so I'm going to reduce it down to a plus c is 7. And then if we eliminate the b terms, then we want to take equation 1 and multiply this times 2 and add it to equation 2. So we'll have 2a minus 2b plus 2c equals 22, and then add that 4a plus 2b plus c equals 5. So we're adding equation 1 and equation 2 together. And see where that gets us. We're eliminating the b's again. So we have 6a and 3c equals 27. And just like equation 4, we'll call this equation 5, but we can reduce it down since all the constants are divisible by 3. That gives us 2a plus c equals 9. So using equation 4 and equation 5, we could say 2a plus c equals 9 for equation 5, and then subtract equation 4. So minus a minus c equals negative 7. That way 1a equals 2. So we have an answer for a. And if a plus c equals 7, then c equals 5. And then let's look at the easiest equation that we started with. How about equation 3? A plus b plus c equals 3. So if a plus b plus c equals 3, then b equals negative 4. So we know our ordered pairs where they crossed was A, B, C. This was the intersection. But remember what we were looking for was the parabola. And the parabola is on the ax squared plus bx plus c general format. And this is our A, and this is our B, and this is the C. So those 3 ordered pairs live on the parabola 2x squared minus 4x plus 5. And I'll let you look at those on your own with your calculator to verify that we didn't make any mistakes. And then our last two examples, those are real life examples. Kyle and Austin are taking the baseball team on a spring break road trip. They plan to rent a van so everyone rides together. Airport Rentals, we'll call that capital A. Airport Rentals has a flat rate of $50 plus 10 cents for every mile that you travel. And Best Auto and Van, we'll call them capital B for Best, has a $30 flat rate, and they charge 15 cents for every mile that you travel. How many miles can the team drive in order to be charged the same amount by the two companies? So we want them to be equal. When will A equal B? So 50 plus a tenth has to be the same as 30 plus 15 cents. So 50 minus 30, that's 20. And 15 minus 10 cents, that's a nickel. And if you divide 20 by 5 cents, then the mileage would have to be 400 miles. So when they drive 400 miles, the charges are identical. Part B, when would it benefit the boys to choose one plan over the other? Well, when they drive more than 400 miles. So if the trip is more than 400 miles, they should choose Plan A, which was called Airport Rentals. Choose Airport Rentals. To be more economical. So that's pretty straightforward. And then our last example is a revenue and cost comparison. We're going to call total cost C of producing X units, and that has two components. We have the cost per unit and any initial cost for a company to start up. When the total revenue, that's capital R, equals the total cost, that's capital C, we call that a break-even point. And this point corresponds to the point of intersection of the cost function and the revenue function. We see that in business calculus. So let's say we have a software developer and they invest $15,000 to produce a package, but they're going to sell that software for $75.25 a piece, and it cost $37.55 for every piece of software that they create. So our cost function is what they invested, $15,000, plus the price to make one unit, so $37.55 for every unit they produce. And the revenue function, that's the money they bring in. So they're going to sell their product for $75.25 for each one they produce. So part B, when will cost equal revenue? That's how they know they've got to make this many and sell this many to break even. And then after that, they've made a profit. So 15,000 plus 37.55 is equal to 75.25. So collecting like terms, the x's, that's 37.70 is equal to 15,000. And on my calculator, I get something like that. So to answer the question, the break-even point, they would need to make 398 pieces of software or whatever they're producing. The break-even point occurs when 398 units are produced and sold. So basically, they don't make any money until they've sold 400 products. Okay, that's the end of lesson 1. I'll be around for lesson 2. Bye.